Okay, so let's go over these quick. Most likely, if you had a question like this on a test, it would be some form of a multiple choice one where you just need to get the answer kind of as fast as possible. What I'm going to do today, though, is introduce some of the properties that we've talked about. Now, the big thing here, when we say evaluate the integral graphically, you have to make the connection that this integral symbol is referring to the area underneath the curve. So I want to go from -3 all the way to 2. So here's -3, and I want to go all the way to 2. But I have a small problem. I end up with a couple of different shapes, right? I've got the triangle down below, and then I've got this trapezoid looking shape right here. So I have to find the area of those pieces. But what I actually want to do, though, is I want to share with you guys the properties that we talked about. What you can really do is you can split this up. Instead of going from -3 to 2, what if I go to 0? And that's kind of what we're going to be doing today. So there's a reason why we're showing you this. You don't have to write this part here. I just need you to know that there's logic and reason behind what we're doing. So I need to find the area of those two shapes. Keep in mind this one is below the x-axis, so we know it's negative. It's a triangle. And the base, if I go from this spot to this spot, I'm going over 1, 2, 3, so I'm going over +4. And I'm going to go down of the height 1, 2, 3, 4. So think of that as a -4. So the area here is -8. And then we're going to add that to the area of the blue shape. Now, yes, you could split this up. You could split this up into a triangle and a rectangle, or you could do a trapezoid. This is actually a trapezoid tilted the other way than what we're used to. So here, base 1 is 2, base 2 is 1, and then the height is 1, 2, 3, 4. Don't get that confused with how we did the LRAMs, RRAMs, and TRAMs, but this is just a trapezoid tipped on its side. So base 1 plus base 2 times the height. That's 3 times 4 is 12. Half of 12 is 6. And the area overall, the large area, is -2. Okay. Now we ask you to do from -3 to 4. Now notice, we already did some of that work, right? So it's kind of important for us to understand that, okay, we've already done this. I just have to find a little bit more. But I do want you to notice one thing here, and this might have tricked you, and that's kind of the reason why I did that. Notice how I start with 4, and then I go to -3, so I'm actually calculating the area going the opposite direction. Well, when that happens, we had the property that was switching the bounds. So what I'm going to do is I'm going to evaluate this in the proper way from -3 to 4 of f of x dx, and the reason why is I have part of that information from the first part, but notice I made it negative. So it's just going to be the opposite sign of what we think. And then officially, if I go from -3 all the way to 4, I'm not going to set this up with rules and split it up. But we know I'd go from here to here, and I know the area for that part is -8. Try to color coordinate this. So this has an area of -8 from -3 to 0. And then I know from here to here, well, that has an area of +6. Ooh, 1, 2, 3, shoot. Good catch, Annika. This is a base of 3. I thank you for that. That changes this answer, this answer, and this answer. And my base is 3, not 4. So actually, this would be -6, which tells me the area here would be 0. Right? 1, 2, 3, 1, 2, 3, 4. I don't think I made any other mistakes. So that has an area of 0, which we can um, if you wanted to split this up, otherwise you know that this area here is 0 because they cover the same amount of space. Well, then I just have to find the area from the remaining piece, which would be from 2 to 4, right? And that would get me to the end of the integral. Well, the nice thing here is this is a rectangle, so I can count 1, 2, 3, 4, 5, 6, 7, 8. That has an area of 8. And since these two add up to 0, the total sum under the area would be a positive 8, right? Because these two basically reduce each other out. So now, what about this part? And this is the thing we said it was kind of a trick, but we want to throw this in there. What happens when I have absolute value, right? We didn't get to talk about this last week, so this is my way of doing it. Absolute value makes everything positive. So I have to go from -2 to 1. And let's see if I can find a nice color that'll pop here. I don't know. Let's try red. So I'm going to go from -2. Actually, you know what? I'm just going to erase this part. So I want to go from -2 to +1. Well, graphically, we know that this part of the equation down here is going to be negative, right? That area is below the x-axis. So one way to think of it is, what if I flipped that area up here? So I went from here to here, and now I am basically finding this area plus this area. And it's just kind of two positive answers. So we've got a base of 2 and a height of 4. That's the first part. That's this triangle that was reflected up. So now it's positive. And then I've got a base of 1 and a height of 4. And then we're going to add those together. So here you get 4 plus 2, and it's a positive 6 because it took what should have been a negative area and made it positive. Okay? So there's other ways to do it, but it's kind of nice to visualize that part flipping up to become positive. There's a question earlier, is this 8 negative? It should be positive because that 8 came from this part of the graph right here, and this part is above the x-axis, so we know that its area should be positive here. Okay, you had questions like this on the Delta Math homework, and one of those was this problem right here. And a couple of people said they had questions on it, so what I decided to do was I did it for you. I did what I would do with it, and I'm just going to show you my work here just to kind of give you a little bit of feedback. So this was one of the questions from the 6-3 Day 1 Delta Math assignment from last week. So kind of take a look at what I did. And I tried to show the properties and all of the work and why it's set up. So overall problem was find the area under the curve from -8 to 7, right? So that's this whole area. And notice, if I split it up, I have from -8 to -2, and that's the red triangle. Now that red triangle is negative, right? Because it's below the x-axis, so we get a -18. Nothing super crazy there. It's just the area of a triangle. And then I took the area from -2 to -1. That's this little triangle right here, right? So this blue area, it's above the x-axis, and it's a 1 by 1. So I got a positive 1/2. Nothing crazy there, but I think the question was right here. Now notice, this is a half circle. It's a semicircle, but it's elevated by this little 1 unit above the x-axis. So what I did was I took and I found the area of this circle first. Now notice, pi r squared is the area of a circle, but I cut it in half. And how do we know the radius? Well, the radius is the center value So I just counted 1, 2, 3, 4. So I've got the area of the circle was 8 pi, but then it was elevated by this rectangle, which is a 1 by 8. So the entire area of the semicircle plus the rectangle was 8 pi plus 8. And then I just have to add all of these together. Keep in mind we can't add pi to the other terms. And then I just ended up turning everything into a decimal. So it had a fraction with a base 2. So then I can combine my like terms. And I'm not positive which way delta math. I believe it accepts both, but I think this might be the best answer. I think you could also write it like this if you wanted. You could say negative 19 plus 16 pi, all divided by 2. But you should be familiar with any answers. I think you could even write it as a decimal. I just wanted to show you that because a lot of kids got confused with what happens. You got to think of this as a composite shape. So a rectangle plus the semicircle, and that's what elevated us above the x-axis. Okay. All right. So we have two things to do today. The first one is just to get a little bit more familiar with the fundamental theorem of calculus part 2. Part 2 is really the big part. And then part 1 is undoing this idea of an integral. And that's what I'll show you here. So we're basically going to do just a couple of review problems from part 1, some ones that are a little more tricky that we're going to start getting into more and more. Quick review though, you don't have to write this because we have this from the previous week, is what if I tell you to evaluate this? What was our process? Well, this symbol, the integral, whoops, I should have an X there. That symbol, the integral, stands for the area under the curve, but we saw the relationship last week that actually if we take this function's antiderivative, which we called capital F, and then evaluated from the upper bound minus the lower bound, it looked like this. Okay? And just remember that this f of x is the antiderivative, and that's why we've been doing the antiderivative for at least a week now. All right, the fundamental theorem part 2 we're going to introduce later, or excuse me, part 1 we're going to introduce a little bit later. So I just want to quick kind of review a couple of these. Since we've done some of these already, it's up to you if you want to write this. I don't want to spend a ton of time on it. So it's up to you if you want to write this down. What I'm going to tell you is these notes will be posted after we get done with it. So you will have time to go back and look at this if you need to. So here's the first thing, the fourth root of x, right? That tricks students all the time. And I have to undo this function. I have to find the antiderivative of it. Well, before I do that, I need to just write that so it's a friendlier manner. And that's usually the step that if students remember that, they're pretty good with it because now it's just a power rule. So remember with our power rule, what did we do? We had to add 1, but this is that creative form of 1. So instead of adding plus 1, I'm going to add a 4 over 4. And notice when I write this, now I'm not putting the integral symbol because I'm taking the antiderivative to say my new exponent is going to be 5 fourths. But as we learned, if I put 5 fourths up top, I have to divide by that, which is the same as timesing by the reciprocal. So there's the antiderivative of x to the 4th. If you're unsure on that, take the derivative of this part and you should get back to where you started. That's the trickiest spot. And the other thing, which actually sometimes occurs more often than you think, is this one. A lot of students forget whose derivative gives me 2. Well, that's 2x. Okay, so here is the antiderivative of the original function. But what about the 16 and the 0? And where did the integral symbol go? The integral symbol actually takes care of, by the antiderivative, the dx is the difference in your x's. So what we're going to do is we're going to turn that integral symbol into a nice straight line. and then we have to evaluate at the upper bound minus the lower bound. So now I'm going to take 16. We always do the top one first, and 16 goes into both of these values. So I'm going to have 4/5, 16 to the 5/4, plus 2 times 16. And then we subtract. You always subtract your upper bound minus your lower bound. And notice I put grouping symbols around there. The grouping symbols don't really mean a lot for the first part. If you forget them for the second part, it could really screw some things up. Well, now I'm going to take 0 and plug them in. And I will say this, if you realize you're plugging 0 into polynomial functions, you could just write that as a 0, okay? But since we're just still learning this process, and some students might really need to just see, 0 goes into both items. I know 0 to any power is 0, so now I'm just going to say, you know what, that whole thing is going to be 0. You can't just omit it. You do have to put minus 0 because that shows that you evaluated the bottom function as well. So just don't get too confident. We want to still show that that is 0. All right, so now the question is, and by the way, this would be a complete no calculator question. Okay, so I know that, let's see, 16 times 2 is 32. And then here the question is 16 to the 5/4. That's side work. I'm going to do that over here. And you have two options. You have the really ugly option, where you could do this. You could do 16 to the 5th power and then take the 4th root. I hope you don't choose to do that because this is without a calculator. That's nasty. That doesn't get us really anywhere. It doesn't help us. So I'm going to take the other option and I'm going to say we're going to pull the 5 out first. Because now 16 to the 1/4 power is the same as the 4th root of 16. And now, if you really wanted to, you could play the divide by 2 game. You can keep dividing by 2, but you know that 2 times 2 times 2 times 2 is 16. So the 4th root of 16 is 2, and then 2 to the 5th power is 32. And yes, they expect you to be able to do all of that without a calculator. And we're hoping that it actually becomes something that is very quick and very friendly. So now, keep in mind that just this part was 16. I did not multiply it yet by 4/5. So it's going to get even more unfriendly. So then I have to do 4 times 32. Well, 4 times 30 is 120. 4 times 2 is 8, so that'll be 128 over 5 plus 32. Well, wait a minute. This has a 5. I'm going to have to add those two together. So I'm going to make this a 5 just so I can add my like terms. 5 times 30 is 150 plus 2 times 5 is 10, so that's 160. And now I can add these together pretty quickly. I get 288 over 5 and then minus the 0. And that's what they expect you to be able to do on the AP test. Okay, and this would probably be a multiple choice question, so you would have to be able to identify this answer. We couldn't just stop right here. All right, so that's just a quick review of how the fundamental theorem of calculus part 2 from last week went. You take the antiderivative and evaluate it at an upper bound minus a lower bound. So what I want to do with this next slide is show you some trickier ones. Okay, and just so you're aware, absolute values, these I've seen on a multiple choice question every once in a while. And it's just something that I want to show it to you quick. If you see it, awesome. If not, I wouldn't worry too much about it. But how can we think of this? Well, we know that 0 to 5, this is the area under the curve. And just think about, what if I plug 0 in? Well, 0 its output will be 4 minus 2 times 0, or 4. So if I go over 0, I'm going to be up here at 4. And then what if I plug 5 in, right? If I plug in 5, I get 4 minus 10. Well, 4 minus 10 is negative 6, but then it's the absolute value, so that would put me up here. So I would have a point over 0 up 4. And then I would have a spot at 5, I would be up 6. Now, what about when x is 2, right? When x is 2, 4 minus 2 times 2 is 4. That would put me at 0. And then if you remember what an absolute value graph looks like, it looks like this. So this is the graph of the function, and we can solve this graphically. Right? I want to just find the area underneath the curve of those two pieces, and that means the same thing. So we have another option, and this is why I'm showing it to you, because this is what it means graphically. Well, wait a minute. What if I took the area under the curve from 0 to 2 of 4 minus 2x? That's this graph right here, right? Well, that we can find very quickly using the antiderivative. And then the only other piece we have to know is, what about this line? Well, this line is actually another graph. It's the opposite of this. And I would go from 2 to 5 of negative 4 minus 2x dx. And that's one of the properties of a absolute value, is this graph actually has a slope of positive 2 and a y-intercept of negative 4. So you could simplify this now. Instead of pulling the negative out, I'm going to distribute the negative. And now watch what happens. We can do each one of these individually using the antiderivatives. Now, to be honest, if this was a multiple choice question, I would solve it graphically. I would graph this, find the area of each piece, and add it up, but it should be equal to the same thing as we have here. So I'll do this really quick. I'm going to take the antiderivatives of these two pieces. We get 4x, that's the antiderivative of 4. This already has a 1, so if I add a 1, I end up with x squared. And if I take the derivative of this, notice the 2 comes down, so I get back where I started. And then I have to evaluate that from 0 to 2. So let's just do that part quick. I plug in the upper bound of 2 minus the lower bound. Now notice, if I plug 0 in here and here, I'm going to get 0. And I know that this is going to show a lot of work, so I'm just going to call that 0 anyways. And then I end up with 8 minus 4, or 4. So this area right here has an area of 4. Well, now we got to find the other piece, which is almost the same antiderivative, but notice this is a negative 4, so whose derivative gives me negative 4? It's negative 4x. And then whose derivative gives me 2x? That's x squared. And we're going to evaluate from 2 to 5. Take the now we'll plug in 5. Now notice on this one, I have to plug in 2, so I've got to subtract, plugging 2 into both x's. And then I can simplify this. We know we get negative 20 minus 25, so that'll be negative 45. And then I get negative 8 plus 4. And negative 8 plus 4 is negative 4, so I get negative 49. Oops, this is minus, so this will be a plus. Let's see, why did that not work out? Oh, sorry, that should be a, nope. Hold on, that's a plus. I accidentally put a negative there. That's a plus 5, so this will be 25 and negative 20, so that'll be a positive 5 here. And then we end up with a minus of a negative 4. So this will be a positive 9. So that means that this area here was a positive 9. And when I add those together, I end up with a total area of 13. So, like I said, this doesn't come up often, and we're actually going to make a connection to this today, and you'll see why. At some point, we're going to teach you how to do all of this in your calculator, so it can be really quick. All right, this one I would like you to write down right here, because this one is very tricky, and it looks really confusing. Okay, but remember, in calculus, just like when we did derivatives, algebra is our best friend, right? Algebra can make things seem a whole lot friendlier. So I don't have a ton of room. I'm going to rewrite this. All right, now the first thing I'm going to do is remember the square root of x, that's the same as x to the 1/2. So the first thing I'll do is we're not changing the bounds, but I've got x minus 2, and each of these pieces are being divided by an x to the 1/2. And if you can do this all in your head, you can skip this first step that I'm doing right here. Okay? Just notice I rewrote this so each piece up top is being divided by its own value. Now that only works when you have a single value on the bottom. If I had like a plus 5 after this, I could not split that up the way I did here. Well, now I'm going to just think of some things, some properties of exponents. Remember, this is x to the first power, but I'm going to call that 2 over 2. And I'm still dealing with just algebra simplifying. I'm not doing any calculus right now. But remember the property? If I had, like, let's say I had x to the 7th over x to the 5th, my rule would, I would subtract the upper bound minus the lower, or the upper exponent minus the lower exponent, and that would turn into x squared. Well, it's the same thing here. Right? We're going to subtract the exponents. So I end up with 2 over 2 minus 1/2 gives me a positive x to the 1/2. That's what this first part turns into. And then here I have a 2 and an x to the 1/2 that's in the denominator, so I'm going to pull it up out of the denominator and now make it a negative exponent. So these are very common themes that you see across the AP questions. We just want you to be really familiar with that algebra. And if you see something that looks really confusing, think about, can you use algebra to rewrite it? Because now this is just kind of a power rule, the same type of work we did over here. What do I have to do? I have to add 1 to the exponent. Now notice I use that creative form of 1. So if I add 1 here, I get x to the 3/2. But if I put a 3/2 up top, I got to put the reciprocal out in front. And then we're going to do the same thing here. I'm going to add 1 up top here, so 2 over 2. And that gives me, now I'm going to keep that original 2 there. And you'll see how I deal with that in a second. But I'll have a positive 1/2 right here. So if I put a positive 1/2 here, I have to multiply by the reciprocal of that, which is 2 over 1. And then the integral symbol, we took the antiderivative, so that symbol goes away. If you were to, by the way, if you were to accidentally write this symbol here, that's wrong. That tells you you'd have to take the antiderivative again, so you have to be careful with your notation. And then I do know that instead of writing 2 times negative 2 over 1, well, 2 times 2 is going to give me 4. And if you're not comfortable or confident in that answer, take the derivative of what you have right here, and you should get back right where you started. Okay? So now it's time to evaluate the bounds. We're going to plug 9 in first. and 9 is going to go into both spots. And then I'm a big fan of, even if you don't need them for everything, but in this case you do, put brackets around it. Because the next thing we're going to do is plug in 1. And it's always the upper bound first and then the lower bound. Now the nice thing is this one is really friendly because it's a 1. 1 to any power is 1, so we get really friendly evaluation here. I know that that's going to be 4, right? But a better way to write 4 in this case with a base 3 is 12 over 3. And then I can subtract 2 minus negative 12 is negative 10 thirds. Notice this subtraction dropped down. This part reduced down to negative 10 thirds. And then the rest of it, maybe we have to do some side work. I'm not sure. Depends how much you can do in your head. I would take the 1/2 first. So maybe you can follow this. Leave the 3 alone, but let's deal with the 1/2. Well, that's a square root. Square root of 9 is 3. 3 to the third power is 27. Right? Now, usually students don't love it when I do that. So I might come over to the side here and say, okay, what did I just do? I took the 3, and I said, we're going to deal with the 3 later. We're going to think of 9 to the 1/2 power. Well, that's the same as the square root. Square root of 9 is 3. 3 to the third power is 27. So that's where this 27 came from. But then I still have to deal with this whole mess, the 2/3. So if I double 27, I get 54 over 3. And then hopefully this is really comfortable. We know what 9 to the 1/2 is 3, right? We did that part inside the parentheses here. So this whole thing is just the square root of 9, or 3. And I get minus 12, negative 4 times 3. But now I want to make sure that this has the same denominator. So instead of putting minus 12, I'm going to turn this into 36 over 3. So that is 12. Just so we don't lose track of where we are, we've got everything has a denominator of 3, which is really helpful. And 54 minus 36 is 18, I believe. 4 minus 36, that's 4. Yeah, 18. And then notice subtraction of a negative turns that into a positive 10 thirds. And then 28 over 3. There we go. So don't get too caught up in that. In my mind, it's not the calculus that's difficult, right? It's all that extra little algebra stuff that they assume you mastered, and it's usually fractional exponents and then dealing with items like 9 to the 3/2. Okay. It's up to you if you want to write this one. This is our last one for, oh, hold on. Yeah, I'm going to do this fairly quick. It's just a little bit tricky. And we haven't gotten into any of the really big tricky ones. That's going to come up after this unit. I just want to show you this. Okay, now we want to think of it as, what in the world is going on here? You could try all the algebra you want, and we can't really do much with this. So what I'm thinking of is, whose derivative gives me this? Right? And it's been a long time since we've done one of these. But the antiderivative, or whose derivative gives me this, if you remember it, is the inverse of tangent. And that's just a fact that if you were to look at you hopefully have that page of derivatives. So look at the tangent inverse, and if you were to undo that, you would get this value right here. Okay. So that's the one tricky thing you just got to be aware of, and now we got to plug this in. We're going to evaluate it at top and bottom. Shoot. Hold on one second. I just gotta. Oh, shoot. Sine, not tangent. My bad. This is the inverse of sine, not tangent, because of the square root. Right? Tangent was 1 over, was just the 1 plus x squared. Definitely didn't bring my A game today. So now the question is, well, I found the antiderivative. I have to evaluate it at the upper and lower bound, and we're just subtracting those. And I do think it's important, even though I don't need them, I should put parentheses around that just so you don't forget. Well, then I'm thinking, all right, I have to undo sine. Now, if you remember the unit circle, okay, I just have sine as being the y value. I'm thinking square root 3 over 2. Well, if I use this part of the unit circle, that's the kind of shorter but longer right triangle. This is at the value of 30 degrees. So I'm thinking, well, whose angle gives me the sine, which is the y value of square root 3 over 2? Those around. Square root 3 over 2 is the long piece, and then I went up 1/2. So whose value, what gave me the square root 3 over 2 for the y value? Is it the 30-degree angle, or is it the one where I go over 1/2 up square root 3 over 2? And in this case, it's the 60-degree one. It's the taller triangle that has the 60-degree angle. Now 60 degrees is the same as pi over 3. And then whose value of sine gives me 1? Well, that is the quadrantial angle, go over 0, up 1. So we know that this location right here is pi over 2. And then those are the values that I would have to subtract. I want to keep them with the same denominator. So I'm going to call this 2 pi over 6 minus a 3 pi over 6. Right? Because I just times this by 3, times this by 2, and then I can subtract, and we actually end up with the value of that integral is negative pi over 6. And we should always deal with it in radians. You don't want to deal with it in degrees. Anyways, we're going to get more into that. I just wanted you to keep that in mind, is sometimes you can't algebraically simplify things, and it doesn't work, and it's just in this case, it was an inverse trig function. So don't get too worried if you didn't see how that was connected, or maybe we need more review of the unit circle or solving. Those are just things we can look at. Okay, I also want to make you exposed to this problem, but I don't want to spend all the time having you guys just write all this down. So let's look at this, and I think it's important to understand what we're doing. Interpreting an integral whose integrand is a rate of change. Well, wait a minute. This actually leads into what we're doing today. First off, it says the population of the United States is growing at a rate of p negative, or p prime is equal to 2.867 times 1.009 t to the power of t. And these are populations in millions since the year of 2015. Well, what we need to do is we need to evaluate this integral of a rate. Well, an integral undoes a rate, which is really interesting. And that's going to lead us into what we're doing today. So I might not do all of this problem because you're going to learn very quickly that this is a perfect calculator question, but we know what the rate is. So P prime is equal to this equation. I'm going to introduce a property today that we're going to talk about on Thursday, Friday. But see this constant, the multiplier? That's not going to change anything. So what you could do is you could actually pull that multiplier out and then evaluate the integral by itself with respect to time. So this should have a dt. So now we're thinking whose derivative gives me 1.009 to the t? And this is a hard one. I can't do, because t is in the exponent, I can't undo this using a power rule. So what I need is I actually need this rule that we had from before. And it was if I had the derivative of a to the power of x, there was always this constant of 1 over ln of a, of the base. And this is just a little special note. If you want to write just this part somewhere, maybe put it on your derivative sheets, you could. That's really helpful. But watch what happens. So I'm going to do the antiderivative of this piece right here. Well, it's in the form of a to the power of some exponent, and its antiderivative is the exact same thing except for we times by a 1 over ln of the base. And the base is 1.009. So instead of writing it as a to the x over that, I'm going to pull that out, and then I'm just going to multiply by its base. Now the plus c, we don't have the plus c because our plus c is taken care of by the 0 to 5. But this would be the antiderivative. Now notice the 2.867, that's a constant. So I just pulled that out and I multiplied the antiderivative by that, and you can completely do that. And then I just have to evaluate it at 5. And then this is the point where you grab your calculator. And I'm going to just really multiply this here. So it's one fraction. And we'll raise that to the 5th power because the 5 will go in first. Now we do have to be careful with the 0, right? If I plug 0 in here, it's not officially a 0, right? Because anything to the 0 power is 1. So I still have to subtract. And there are multiple ways you could do this, but I'm going to plug 0 in like this. Okay? And again, now it's all calculator based. Plug this into your calculator. We know that anything to the 0 power is 1. And then we can simplify each piece and we'll get our answer. So you get that. Nothing super crazy. I just wanted to show you that when you have a problem like this here, and it's the base raised to the power of the exponent, we have to use the special antiderivative. We're not going to do B and C. We'll come back to those at a later time. All right, so that's the first part. The second part here is we're going to use this to lead us into it. And I definitely want you to write this part right here. You don't have to write what's written in black. It says, use the fundamental theorem of calculus part 2 to evaluate the integral. A hint is, remember, use the antiderivative, evaluate it at the upper bound minus the lower bound. So nothing really crazy. It's actually a really friendly antiderivative. What I'd like to do, though, is we're going to do a property here. So only write the blue part. And the first thing we're going to do is we're going to take this 3. See that 3? It's a multiplier. I'm going to pull it to the outside. You can do that with any multiplier. But notice something in this problem now. Instead of going to 2 different numbers, we're going to x. Okay. Now that's just a little bit tricky, but we'll deal with that when it comes up. So that 3 is going to be a multiplier. And then I have to take the antiderivative. Well, whose derivative gives me cosine? The derivative of cosine, the derivative of sine is cosine. So this is a very friendly antiderivative. And we're not going to put a plus c because we have bounds. And anytime you have bounds, now we got to evaluate them. And nothing really crazy either here. In this case, I get 3 sine of x, that's the upper bound, minus the lower bound, 3 sine of pi over 2. And then we can simplify this part. Right? We know that the sine of pi over 2 is 1. And then 3 times 1 is 3. So that's as far as I can get. But notice they said, let's let y equal that. So there's my answer. Nothing crazy, right? But the new part today says, let's take the derivative of this. Okay, what happens when I take the derivative of an integral? Right? So I could do all this work, and I know what the function is. This is the original function from x to pi over 2. Now remember how we didn't put plus c here, and the reason why? Here's the c. That's a constant. It was formed by the bounds. But now, what if I take the derivative of this? So dy dx, well, the derivative of 3 of sine of x, the 3 is a constant, that's going to stay. The derivative of sine is cosine, and the derivative of minus 3 is 0. Okay, well, why is that important? Look at my answer. The derivative of this function right here is the exact same thing. The only difference is this x was put right in there for the t. So what that actually tells us is we could have skipped all of this work if all I wanted to do was find the derivative. I don't have to evaluate the integral because the derivative and the integral are going to reduce each other out. But there is something very special with this x that goes in here. Because what would happen if I change this to like a 2x? Okay, don't write this, but watch what happens. What if I plug this in as a 2x? So I make this a 2x, and that's a 2x, and then I would put a 2x right here. Right? That's a 2x. And then when I evaluate that, I would get a 2x here. But then when I took the derivative of that, I would have to have the chain rule, right? The derivative of this 2 on the inside would come out, and that would make this a 6, or a 2, it would be double that. So what we're going to talk about next, we have to be careful if it's more than just an x, the chain rule applies on the outside. Right? I'll show you that here. I don't want that original 2 to be in my notes though. Okay, so here's what we got. Don't write this because it's just a theory. This is just a fancy way of saying that, you know what? The derivative and the integral are inverse operations of each other. They cancel each other out. So here's what the fundamental theorem of calculus part 1 says. Again, don't write it. Suppose f is a function that is continuous on a closed interval from a to b, and I, they just picked I, it doesn't matter, but I is denoted by the integral from a to x. Now, x is a variable, but a is a number. It's part of our piece. Well, what happens if I took the derivative of this? The derivative of both sides, the derivative of I is I prime, and then I would take the derivative of this function, and the d dx is actually going to reduce this integral out, and the only thing is this x now goes in where the variable was before, and you're left with the original function. So the derivative and the integral are inverse operations of each other. I hate to say it, but they cancel each other out. Okay. Now, why does this work? Okay, here's a quick little explanation, and let's look at what happens. In purple, I have my original integral. Well, what if I took the derivative of that? I wanted to take the derivative of that. Now notice, if I take the purple and I evaluate it, so I get capital F, that's the antiderivative, evaluated at x and at a. Now remember, a is just a number, right? This isn't a divide by a number. This is saying that f of a is going to be a constant. F of a is going to be a constant. F of x is a variable, right? So this is going to give us an equation, and I still want to take the derivative of it. Well, the derivative of an integral gets me right back to the function itself, and the derivative of a constant is 0. So I'm right back to the original function. Now, you might not feel comfortable with this because it's pretty mathy right now. Let's look at this example. Okay, I'm going to do 2 ways to do this problem. Well, let's see. Let's do the easy way first. I'll have you write this, and then we're going to find y prime. Remember, that's the same as dy dx. Okay? So what do they want us to do? They want me to find the derivative of this piece. So what do? Well, we're going to take the derivative with respect to x to both sides. And I'm going to see if they'll let me, I want to squeeze a dx right here. Okay. When I take the derivative of y, we just get dy dx, right? Which is the same as y prime. And then if I take the derivative of the integral, now there has to be one special thing. Your bottom value right here must be a constant. Okay, and -3 is a constant. This one is, the variable should be up top. If it's not, remember we can flip the bounds and you can make the opposite sign. So I'm not too worried about that. But what happens then is the derivative and the integral, they're going to reduce each other out, and all you do is take, because this 3 will be a constant and the derivative of the constant is 0, you're just going to plug in x wherever there's a w, and your derivative is that value. It's that easy. Okay. I'm going to show you with a easier or a friendlier example why that works. You don't have to write this one down if you don't want to. Let's say I go from, you know what, let's do this. Let's go 5x, and we'll go let's say negative sign of x dx. So I'm purposely making this one much friendlier. Now, if you want to do this one the long way, right, they still want us to find the derivative. So I have to take dy dx, or dx of both sides. Okay? But let's say that I didn't want to do that and I just wanted to evaluate this first. Well, you're going to notice one thing here. Notice how that x is on the bottom. We don't really want that, but if I did it this way, watch what happens. If I took the antiderivative, right, whose derivative gives me negative sign? It's cosine. And this should be something other than an x, maybe a t. So let's call that d. Let's call it t, just for fun. So whose derivative gives me negative sign of t? That's positive cosine. And then I'm going to evaluate it from 5 to x. Now keep in mind, I did not take the derivative of that yet. I'm going to do that at the end. I'm just going to keep that red derivative piece on the outside the whole time. Okay. Well, now, what if I plug in cosine of 5, and then I subtract cosine of x? Okay. Well, now, I don't care cosine of 5. That's a number, right? This value right here is just a number. So what's left over then is I still need to take the derivative, that's why the red part has been here, of negative cosine. Because this, well, maybe I'll do this. We've learned that with derivatives, we can take the derivative of each piece individually, right? So I can take the derivative of this part, and I can take the derivative of this part. Notice how I just pulled the subtraction out. That's fine. But now, since this is just a number, cosine of 5 is some number, it's a decimal number in our calculator, the derivative of that number is 0. Nothing crazy there. But then whose derivative gives me cosine? The derivative of cosine? Well, that's negative sign. And what happens is I get 0 minus negative sign, or positive sign of x. Now, that is a long way. That's a long way of taking and doing this work. dy dx, because the derivative of y is dy dx. So, isn't there a shortcut? Isn't there a faster way to do this? Let me just show you this faster way. If you have x on the bottom and 5 up top of negative sign of t dt. Okay. First thing I'm going to notice is, see how this answer right here, positive sign that we got, is not identical to the original value. It's off by a negative. The reason why is the x is not on top. So first thing I'm going to do, if I'm going to use a shortcut, the first thing I'm going to do is I'm going to flip the bounds. So I'm going to put x up here and 5 right here. And then I'll take the opposite of that. Now notice that negative and this negative, you could reduce those right away and get a positive answer if you wanted to. Okay? But there's a fast rule now that says if I want to take the derivative of this whole thing, well, this derivative is going to reduce out with the integral, and what's left over is this value plugged in. So I get the negative, the red negative, of whatever the function was with that x plugged in. Now, do notice a negative and a negative reduce out to be a positive. And there is a faster way of doing it. And that is the fundamental theorem of calculus part 1. It's saying that the derivative and the integral are going to reduce each other out, and whatever your function was in the underneath the integral, you're just going to plug in that x value. Okay. Now notice, the long way got me the same answer, positive sign. The short way got me the same answer. Okay, let's try this one, because it looks scary. But we're only going to do the shortcut on this. Fundamental theorem of calculus part 1. Shortcut. All right, so what do we have? We've got y equals an integral. And then they say find the derivative. So I want to take the derivative of both sides. But before I do that, we don't like x on the bottom, right? So we want to flip the bounds. I'll just do that in the very first step. So what I'm going to do is just rewrite this exactly the way it is. Now notice, see how it's v instead of t? That's fine. They call that a dummy variable because we're going to plug in x anyways. But I have to have x. I have to have x on top for this to work the way we want it to. So all I did was flip the bounds. Right? So now I'm going to take the derivative of both sides. And instead of doing all this by hand, right? Instead of doing all of this, which is a really nasty antiderivative, all I'm going to do is take the 5x. We're going to plug it in where the variable goes. And don't forget that we flipped the bounds and made it negative, so that negative has to appear. But there's one other thing. We have to, because there's a 5 here, and I just put in a new 5 into this function, if I was to take the derivative of that, remember how there's a chain rule that comes out? So we got to multiply by the chain rule. We're going to multiply the entire function. And that's it. It's super quick. And it just basically says that this derivative is going to reduce out the integral. That's it. I don't think we're going to get to these. I put a lot more in here. Um, let's do one last one just so I know you're confident in it. And I'd like you to try this. Let's say that y is equal to 4 to the 4 to 3x squared of the 5 to the, let's say, t power plus 2 t minus 4 dt. Okay, so I give you that integral and ask you to find y prime. Or I could say find dy dx. Well, what we know is that if I'm going to take the derivative of both sides, we know that the derivative of y is y prime, or you could write dy dx. Remember, those are the same. But then here's the fundamental theorem of calculus that says we know a derivative and an integral are going to reduce each other out, right? Those are gone. The only thing we have to do then is we have to plug in the variable, the 4. Now, a lot of times people are like, well, what about the 4? If I plug the 4 in here, here, and here, that would give me a constant. And if I take the derivative of the constant, this goes away as well. So just remember, that's a constant when it's plugged in, and the derivative of a constant is 0, so it's not there. So the only thing that we have to do is we have to plug in a 3x squared wherever there's a t value. Now notice, there isn't a t here, this is just the minus 4. So this answer will be 5 to the power of 3x squared plus 2 times whatever t is. In this case, t is being replaced by 3x squared minus 4, right? That minus 4 does not have a t, so we don't plug it in, but we have to include it. And the last thing is we have to times by whatever the derivative of this is. Because that, notice, see how we put in a 3x squared into both spots? If I was to take the derivative of this, there would be a multiplier out here by that derivative. So I have to multiply by the derivative of whatever 3x squared is, which in this case is just 6x. And you could leave it just like this. You don't have to simplify it. If you wanted to, you could distribute a power here, but it's not really going to make it do anything better or it look any better. Okay, it looks way more confusing than it is. So here's what we got today. We're going to do these problems here next Thursday. Your homework tonight is actually to take a quiz. And the reason why is we need to get one more quiz in here before we can move on. And this is just a logically great spot for it. So what you're going to do is you're going to take the quiz for homework tonight. Okay, there is no other homework than taking the quiz, and it's in Schoology. Remember to show your work on a separate sheet of paper because we're going to have you submit some of those images. So show all work. And then for Wednesday, Wednesday's work is to watch the Ed Puzzle video that introduces Thursday's lesson. And we're actually going to teach you how to do some of this stuff in your calculator through that video. So you definitely want to watch that on Wednesday. And we're going to review a problem like this one, where what happens if I have an x in both spots and they ask me to find the derivative? How do we deal with that? So That will be on Wednesday. And then just a friendly reminder, our test will be assigned next Thursday, Friday. So the 11th and the 12th. And then it's going to be, you'll have the weekend to do it. And it'll be due on, is that President's Day? Yeah, President's Day. You don't have school on Monday, but that's when it's due. So just so you can plan ahead, and with that being said, all missing work will need to be in on that Wednesday, the 10th, February 10th. So get your work in.